Last time we spoke about the new website for Imandra X, and again, would highly recommend it if you go to imandrax.dev and just go through documentation, and more importantly, install the Visual Studio Code. And I keep forgetting what the open source equivalent of the Visual Studio marketplaces, but basically this extension works in the VS Code and also in other IDEs like Cursor, Anti-Gravity, etc. And then to get going with CodeLogician, again, go to codelogician.dev. There you'll see your the install script. You install it once, and then basically when we update it, it'll prompt you if there's a update that's available. So so yeah, get that going. And then we have gone last time through doc and eval commands. So check out the video that's, I think it's on codelogician.dev and maybe on imandra.ai both. So definitely on our YouTube channel to get going with those commands. And then what I wanted to go through today is two things. First, go through more of kind of real world examples. So on the CL, short for CodeLogician Dev website, we had a number of industrial case studies. They are all now in this publicly available repo called CodeLogician Demos. So if you want to follow along at home, just go to this address and yeah, I'll go through that. And then as promised before, we're going to do a bit of a sneak preview of what's about to be released soon, which is CodeLogician Trace or Traces. We haven't figured that out yet, but it's going to be, I think, pretty cool and exciting, and I'm sure you will enjoy it. So let me now go to, I'll just start to share the whole screen so we can okay. So, and let me go through this stuff right here. So this is the demos repository. So the first one I wanted to do is to look at nice. So again, this is all in the demos GitHub repository. You can go through it, etc. But I wanted to go through some kind of more concrete use cases of what you can do with CodeLogician, where this adds value. So this is bank account classification demo, which Paul Brennan, our chief strategy officer, has kindly put together a while back. And it's really great at showcasing how few additional lines of code can significantly increase the complexity of the code that we're analyzing in ways that LLMs alone would never be able to pick up. And let me just make this bigger. So I wanted to go through kind of the setup and then walk you through the resulting IML model. And we can also get Claude to basically convert this, and we can do all of those things as well. But I wanted to kind of showcase the kind of the business side of these things, the applied side. All right. So why don't we just go through this kind of business problem? So obviously within a bank, there's lots of regulations, lots of requirements, especially when it comes to different fee schedules and how interest is calculated, so forth. How you can, it sounds simple, but once you have money going in and out and of a basically bank account with different payments, deposits, withdrawals, etc., and different criteria for when, let's say, if you just park money in the bank account, you have, let's say, it's supposed to be accruing interest. So how do you calculate that interest? Again, depending on all of these kind of actions that can happen within the bank account. So this demo goes through how you kind of classify and different product types, and again, so all of this kind of complexity. And this enhanced version, I'll keep going to this thing. So this advanced version of the model itself or the business requirement just adds some logic on what the threshold kind of levels are around average 30-day balance. Again, so there's also things like what's the average? How do you compute that average? Is it arithmetic? Do you count for weekends, etc.? So lots of kind of complexity. And again, all of these things are they have to be done within various regulations that all of the basically all banks have to abide by. So if we go and we ask, effectively, Claude to go and take let's say this business, this basic logic, and basically express this logic as an IML model, we'll get something like this. So again, you have these are just how you would define types, algebraic data types, and IML. You have transaction types, interest, all of these things. This account type here represents what is in the account. So you can see kind of counterparty identifier, deal product type. Again, so this here we're building out these type definitions. And then some critical functions. You can define, is a product eligible? Is this transaction type? Is it depositor initiated, etc.? So we're getting more and more inside these various complexities of basically these details that we have. And if we go down to the logic here, the stuff that we want to analyze, you can see this analyze transactional account. So this decomp top, this is the decomposition command that tells Imandra to go and analyze all of the different edge cases. So when we're talking about regions and, for example, here, like what are all of these edge cases? Let's say 21% more code created 190% more complexity. This is what we mean by that. So when we have, this is the original function, and when we run decomposition top, this is just calling it on this function here. This is just a syntax. We get a certain number of edge cases. And when we go to the more advanced model, this number of edge cases will kind of increase. And the edge cases, again, are just due to various kind of, again, complexities when it comes to these product types and different fee schedules, etc. One kind of interesting thing here is you have these functions that, for example, compare date. So typically, like when you're comparing dates, you would write something like LEQ, which is short for less than or equal to. So you can see here, let's say you have let's say you have a function that compares as part of the computation 2 dates. And there's a number of ways that 2 dates can be different. Obviously, you can year, month, etc., day, time, including hours, seconds, etc. So you can see here, there's a lot of kind of details that go into this stuff. And when you want to analyze regions, so how many edge cases are there, let's say in a function or in a model that involves this type of computation, by default, you will get something out that consider all of those edge cases, because technically, let's say you were just compare two transactions, and you want to understand, in what ways can they be different. Again, transaction can have associated attributes like counterparty, etc. So if they both have dates, and we have the kind of let's say default function that looks at all the different edge cases, how 2 dates can be different, you're going to get this kind of a big edge case. I won't say explosion, but it's not going to explode, but it will give you all of these possible ways that 2 days can be different. But what typically will happen is things like this, you may not be interested in exploring all of these edge cases. You just want to say, okay, let's say I want to focus on, let's say, these transactions, but only just tell me if, give me edge cases where the dates are different. I don't care how. Don't enumerate for me that the dates can be different because of year or because of microseconds. So for that, we have this concept of a basis. So you can add basis as an attribute to decomposition request, and there you can enumerate functions that should be in the basis. So think of that as something that will just be kind of treated by decomposition as a kind of a whole entity. It's not going to be looked into specifically. So if you add to decomposition this, let's say, date LAQ, and you run it, what you'll get as an output is just kind of regions where if they're different, it's not going to open it up. It'll just say, okay, the LAQ is false or true, etc., without giving you the full details. And this is really important when you're modeling really complex systems where, let's say, you're comparing lots of orders, etc., and all of them have associated timestamps. You don't want to go and really compute all truly the different ways that, let's say, 10 orders and each one has, timestamp, how they all can be different, because that will take into account all of these different details. And so, yeah, that's just more of a kind of industrial knowledge for how to really scale these formal techniques to really complex systems. And this, if you go to imandrax.dev, under documentation, under region composition, you will see um, this concept of a basis. And there are other things like side conditions, etc., that you can also look into that all further allow you to really become surgical with these functions. Okay, so this is the base one. Let's also look at now the more complicated one. So you can see here, this is now, the code grew by 21%, but behavioral regions grew 190%. So you can see there is more basically logic here that now looks at predicted balance threshold. And let's try to visualize this. So you can see that this is basically significantly bigger now. Yeah. Okay. So if you want to follow this along, basically you can just execute these. So you should have CodeLogician. So this is actually, I'm going to change that. This is referring to lights, which you already should have, but it's better to just use the main one. CodeLogician check and accounts enhance. So both of those files are in that repository, and you should just be able to run them with CodeLogician. That's all. Okay, so that is one. Let us now go through this other margin account. Okay, so margin accounts in finance, and I apologize, most of these examples, because we're coming from finance world, but this will typically contain a lot of finance related examples. But margins are basically accounts when you're trading through, let's say, a broker or on an exchange. You need to maintain a certain amount with them, because you need to place a certain amount of money with those institutions. So they kind of basically, they know that you have cash, and if your positions that you take through them incur losses, they can always withdraw it without having to look for you and try to basically get the money out of you. So this is what these kind of margin accounts are. And you can see here is leverage trading accounts. This is leverage accounts is when you basically borrow money from, let's say, a bank or broker to trade. As you can imagine, making sure that the accounts are up to date and are valid with respect to what you can kind of post on these margins. So the reason is, it's not necessary that you have to put in the cash only. You can, for example, park various assets. So if you have treasuries or different types of assets, you can still park them with that broker, and they will count towards these kind of margin requirements. You can see here is there was a big case with this. I think it was a hedge fund in 2021 where these margin accounts were not enforced adequately. So the systems and controls, aka software, in these institutions just effectively fail to recognize that this customer did not have sufficient margin in the bank or broker. So you can see here, these are different, effectively, different positions that someone can take. And you can see here after 40% market decline. So this is the original one. So let's say there's a 40% market decline. This has basically collapsed and liquidation call. So this is when an institution decides to say, okay, we now, like the positions that were taken are so they're losing so much money, we actually need to go and claw back the different assets. So we can, because effectively when you're trading through a bank or broker, you don't have the license to trade on the markets. You're doing it through them. So they're using their license to effectively trade on your behalf, but they're on the risk. So if, let's say, you take on positions that lose a lot of money, ultimately they're the ones that have to basically provide or pay whoever they bought the positions from. And if they can recover this money from you, then they will have to use their own resources for that, which they do not want to do. So this is a way of kind of a stop loss mechanism for saying, okay, we have a customer that traded with us. Now they're losing lots of money. We need to, if we can get enough money from them right now, we're going to have to end up paying that money ourselves. So this liquidation call is effectively just a way to kick off that process. And again, as you can imagine, all of these different rules and procedures have to be very precise. And this example that's given here basically just says this, okay, when software had a glitch, in these kind of rare situations, a lot of money was lost. Because in case $10 plus billion. Prime brokers, this is typically referring to a bank because they fail to adequately enforce these rules that they had on the books. So this right here is basically IML model. And when we write this logic, what we can do with Imandra is mathematically verify that basically this engine, this logic is actually working as we expected. So not kind of, perform property testing or random testing or just human testing, etc. We can actually mathematically produce proof that this is correct. So this is the first one, and the second one is also basically, this is just showing us, okay, you can see here, verify is they're very similar in what they do. This here looks to mathematically verify that this function, this input function, is true for all instances. And if not, it will typically produce a counterexample. This instance specifically looks for a case where this is false. So you can see here, this is true. So we have the smiley Imandra face. And then this instance is false where it's going to check this, but it should maybe produce this. Maybe I was just printing this incorrectly, but this instance will get you this case where this is basically, you get this counterexample altogether. So, and yes, this is how you would basically get that check verification goal. So check VG will get you both of those guys printed out. Okay, so we have this. Last time we focused on, actually one of the kind of the examples that I think went through is the Stripe example of formalizing something and then using Imandra X to check the logic and then identifying edge cases, etc. So what what stood out from that is, and there was a nice Medium article on this already, what really stood out is there is a lot of kind of computation, a lot of decision making that happens, but it's really difficult to observe it, or it's really difficult to send this to someone so they can actually check this themselves. Because ultimately, if you think about it, let's say I have a repository, I'm writing code there using LLMs. So there's a lot of heavy context engineering or prompt engineering, etc. I have my own context. And then lots of code gets written. Then it is committed, it is pushed, and then I tell you, hey, check out the GitHub repository, etc. And it's kind of like it's a good example of how really coding is now being performed. And I think where a lot of stress and a lot of, let's say, anxiety comes from, because a lot of coders are now using LLMs. They kind of give these instructions. Lots of code is written, it is pushed, and then you have people that are supposed to be reviewing that code. First of all, the volume is just significantly increased, so there are fundamental capacity issues. But also, if you think about it, typically people don't want to go through LLM generated code. So you have this kind of call of theater where one group of people uses LLMs to write code, but they pretend they don't. And then it is shifted on to another group of people that are supposed to be reviewing this code, but they don't. They'll typically say, looks good, etc. So how can we effectively change this? How can we adapt ourselves to this new paradigm where a lot of the code is auto-written, but we still want to have effectively governance and really a way for us to understand how, what things are going through. And something that we're really excited about is what we'll call CodeLogician trace or traces. But it's effectively, it's a way for us to kind of visualize the different artifacts and the decisions and the reasoning and the different reasoning steps and that took place by, let's say, LLM agent. And so that you're not, as a human, you're effectively no longer just looking at GitHub commits and the diffs, etc., but you're reasoning about what these changes are at a higher level. So and clearly you want to bring in kind of mathematical logic into this. And so that's what CodeLogician Trace is supposed to bring out. It's supposed to allow you to, first of all, make sure that when you're writing code, your CodeLogician is kind of staying in its lane, and the code that it writes is based on logic in a way where it can actually describe it. And more importantly, when you have this AI generate code and you're submitting it to someone else, they have the ability to first visually inspect and kind of understand that, okay, what was the logic that came into this change, and make sure that, let's say, any output or any test case modifications, etc., were actually grounded in thorough reasoning and not just kind of, you know, um, effectively just hallucinating code, etc. So what will be, I'll show you a demo just a second. But this is the kind of the big idea is when with CodeLogician, what you'll soon be able to do is get your LLM to really structure its reasoning for code to describe what all of these different changes are and really create this model that will have all of these different artifacts. So let me go to. But okay, so this is the Stripe example. Again, you can look at our Medium page, but this is something I went through last week. You can see effectively a way. So there is a JSON format that this contains, but the big idea is LLM writes some code, and let's say lots of changes. And instead of going through these changes kind of yourself in GitHub or pretending that you go through them and just kind of accept the changes, etc., you want to be able to navigate through these different steps and make sure that the changes that are produced are backed by actual thorough and rigorous reasoning grounded in logic. So this right here is representing what this will look like. So we'll push this out as kind of standalone dashboard, or actually not or, and a VS Code extension. So imagine, you get a basically pull request, and there you're going to have this JSON with CodeLogician trace that you can open up with VS Code extension. And you can see here, this is just, so it's not necessarily that we're just having the formal reasoning steps, but it will have other steps as well. So for example, research, kind of what the LLM was doing. So it was analyzing state machine, etc. Then it actually kicked in formal reasoning logic. So in that case of Stripe example, it converted this Python code, it formalized it into basically this IML code right here. Then it started to write verification goals. And here, basically, this verification goal that it wrote right here, it basically found a counterexample to here. So you can see here, then it was, it found this issue in the model, in the logic, and then basically made a fix. And then the next step is introducing this more complex logic, 3DS, which deals with kind of more advanced security features of Stripe. And here you can see this original capture. So this is the original model before this change. So here it basically updated the model and then defined these different verification goals that have to be satisfied. So basically, again, so if you can kind of follow through the steps, it had a problem. It formalized the code into an IML model. It then effectively made the change to the IML model to take this into account, this new kind of feature, and then wrote out these verification goals that should be satisfied of the new model itself. So it's basically converting requirements into formal logic here. Here, it is basically just went out and used Imandra to verify them. So you can see all of these things are proved. And then, okay, so this is adding more logic. It is then verifying it. And yeah, so lots of, you can see here, so it's kind of going through steps. And here, for example, it is now running through region decomposition and making sure that it can actually kind of understands what the new edge cases are in this new system. And from those edge cases, it is generating basically test cases. Again, this is all using CodeLogician from this guy. And so then it has this basically precise mathematical model that it knows what the edge cases are, it verified the new requirements, etc. It is then updating this Python code. You can see here, you can see this evidence, etc. And then you can see here a verification step. It is then applying these 84 test cases that were generating at the modeling stage into the code that was verified. And then you can see here at version control, it is then basically committing everything into the repository. So the idea is we're going to add a bit of bells and whistles to further formalize this into something that kind of has more formal feel to it. So, but this is the big idea. So you can actually say, okay, this is the formal reasoning that was performed. Yeah. So you can actually trace what the system was doing and with different kind of artifacts. And you can see here, we're also kind of working on these steps. So the idea is, let me just go through this. So any type of artifact that's produced as a kind of outcome of this process, you always want to be able to kind of diagnose and say, okay, well, okay, let's say some code was written to do something. What were all of the different steps, and what is the data flow that was involved and ultimately led to this stuff? So you can see here, this is like the last kind of step of, let me just go through this. Yeah, so this is commit 3DS. Let me see this. Oh yeah, so here's the guy. So you can see this is the last step, and all of these basically all of these guys led to that. And the reason for this is, as you obviously know, the agents today are doing lots of things in parallel. So as they're producing these things, you might have this big graph, but fundamentally you say, okay, this thing wrote 3 new edge cases or 3 new test cases. Let me actually navigate and understand what are all of the steps that led to this, whether it's kind of researching, identifying what the code blocks are, or etc. And so where all of this is going is we want to kind of live in a world where we can create policies and make sure that these processes abide by them. So if, especially this is true if you're in an enterprise or regulated environment and you want to say, okay, all of this code is going to be written, but I need to have precise artifacts that demonstrate thorough, rigorous reasoning why this test case was added or why this feature is, let's say, in compliance with, let's say regulations, etc., what the artifacts are for making those changes. And so this is what this kind of shows us, this ability to gather all of these different things and actually say, okay, this is what kind of transpired. So before this, if you go to the Medium page with Stripe, you'll see that, I just basically describe it. Hey, I got some code. I did some stuff with Claude and CodeLogician, and then here's a snippet of what it produced. And then this other thing that happened, it made it better. And then there's a lot of English prose that describes it. But what we want to be able to do is to actually share, okay, actually, here's what precisely happened. And so anybody can investigate this instead of kind of trying to pretend that they go through GitHub changes. They'll actually say, okay, so all of these things are within policy. It looks like they're sound. And, we have actual evidence that the changes that are produced are in compliance with regulations or requirements, etc., like this. So it's not just folks like PR messages and things like this. So this is what we're working on. There are a couple other things, namely CodeLogician, which we will get out soon as well. So that kind of allows you to build out these large models of, especially in finance, it's really relevant because there's a lot of legacy code that, it goes back to COBOL. 10 years ago when I was working at the bank, there was still stuff that was written from early 90s, these kind of middle office and back office systems that just kind of work and nobody wants to touch them because if you touch them, they can break and no one knows how they precisely operate internally. Everyone that wrote them kind of has a long time ago moved on. So in banking, I would imagine that would be a very big kind of use case for this. But yeah, so traces, this is what we're going to go out in public, I think tomorrow or maybe early next week. But on these weekly reasoning calls, you're always ahead of the curve. You're seeing things before they unfold. And we think that this is hopefully will resonate a lot with developers that are right now trying to struggle with the amount of code that's written. Okay. Awesome, guys. Well, thank you very much for this session. And I will leave you with this kind of sign. And if ever have any questions, please reach out to us. And looking forward to the next one.